In this video, I'm going to go through the first midterm review packet that's all about transformations. So for number one, it says, if A prime, B prime, C prime is the image of triangle ABC, under which transformation would the triangles not be congruent? Remember, if the triangles aren't congruent, that means when you transform them, you did something that wasn't a rigid motion, which, remember, rigid motions preserve angle measure and side length. So a reflection's a rigid motion, so that can't be it. A translation, just moving something left, right, up, down, that's a rigid motion. A rotation, spinning something around, is a rigid motion. But a dilation, centered at the origin with a scale factor of 2, remember that's, let's say if I've got that triangle, and then I dilate it by a scale factor of 2, it would double in size. So all of a sudden these side lengths are no longer congruent. So anytime you have a dilation, the images will not be congruent. Similarly for number 2, it says the vertices of triangle JKL have those coordinates, under which transformation is the image not congruent. And again, a rotation, a translation, and a reflection are all rigid motions. The only thing that isn't is a dilation. Number 3. In the diagram below, a square is graphed in the coordinate plane. A reflection over which line does not carry the square onto itself? Well, let's try a couple of these. For x equals 5, that's if I go right 5 and draw a vertical line there, well, I can already see that if I reflect over this line, this square is going to end up on this side of the line, so it's going to be somewhere over here. So it's not going to land on top of itself. So I already know that's the answer. But if you wanted to check a couple more of them, y equals 2 is just going up 2, that's the horizontal line there. And that's a line of symmetry for the square. So if I fold it over, this side is going to land on this side is going to land on this side, and so on. For y equals x, that's that diagonal line that goes straight through the origin, where all the x and y values are the same. So that is also a line of symmetry along the diagonal. And then for number 4, if I end up subtracting x on both sides, I'm left with y equals negative x plus 4. So that's a line with a y-intercept of 1, 2, 3, 4, right up there, and with a slope of negative 1. Of course, you could always type that into your calculator. And that goes along the other diagonal there, and that's also a line of symmetry, so the square would carry onto itself over that transformation. For number 4, a sequence of transformations maps rectangle ABCD onto rectangle A double prime, B double prime, C double prime, D double prime, as shown below. And it asks which sequence of transformations is going on here that maps this to this and then this to this. Well, remember that the corresponding vertices need to match up. So D needs to end up at D prime and C needs to end up at C prime and so on. So this first transformation looks like I reflected it right over the x-axis. So I know it's got to start with a reflection, so I could rule out 3 and 4. And then to get from here to here, it looks like I spun it in a counterclockwise rotation, so that's going to be a reflection followed by a rotation. Number 5. Which regular polygon has a minimum of 45 degrees to carry the polygon onto itself? Well, remember, an octagon has 8 sides, a decagon has 10 sides, hexagon has 6, and a pentagon has 5. So what you could do to check is you could take 360 degrees and divide it by the number of sides, and that's going to tell you the minimum degree rotation for it to land on top of itself for all those sides to line up again. And if you take 360 divided by 8, you get 45 degrees. So it must be that it's the octagon that takes 45 degrees to carry on to itself. And you could try that through all of them if it's not answer choice 1. You could divide 360 by 10, divide 360 by 6, and so on. Similarly, for number 6, it says which rotation about its center would carry a regular decagon, remember that's 10 sides, onto itself. Well, if I take 360 degrees, a full rotation, and divide it by the 10 sides, every time I spin it 36 degrees, I'm going to end up right on top of itself again. So the idea is all of these are not multiples of 36 except for one of them. So a 36-degree rotation would land on top of itself, but so would a 72-degree rotation. That's just 36 times 2 36-degree rotations. So what you could do here to quickly check is you could divide all of these by 36 and see which one gets you an even integer so that it's a multiple of 36. And when you divide 252 by 36, that's 7 rotations of 36 degrees, so that would land the decagon right on top of itself. The rest of these are going to be decimal answers, so they're not full 36-degree rotations. Number 7. On the set of axes to the right, rectangle ABCD can be proven congruent to rectangle KLMN under which transformation? Now, this is a tricky one because if you're looking at the picture, you might think, oh, I just rotated it clockwise a little bit. But if I'm looking at the rectangle ABCD, and I want to know what proves it congruent to LM or KLMN, that's telling me that A needs to map onto K, B needs to map onto L, C needs to map onto M, and D needs to map onto N. So in order to get A to K, and N to D, and B to L, and C to M, I would have to reflect it over the x-axis. A rotation wouldn't help me there because it would send A to N, but I know A needs to go to K because of the order of the letters that they gave me. So to me, that's going to be a reflection over the x-axis. Number 8. After a reflection over a line, triangle A prime B prime C prime is the image of triangle ABC. Explain why triangle ABC is congruent to triangle A prime B prime C prime. Well, you know a reflection is a rigid motion. So the first thing you could say is that a reflection is a rigid motion, and rigid motions preserve distance and angle measures. So that's a phrase right there that's going to be helpful anytime you're talking about rigid motions and congruency. So the side lengths stay the same and the angles stay the same as well. For number 9, triangle ABC is graphed on the set of axes below. Graph and label triangle A prime B prime C prime after it's reflected over the line x equals 1. So that's just a vertical line where all of the x values are 1. So here you could just count. B is 1 unit away from the line, so B prime would be 1 unit away. C is 1 unit away as well, so C prime would be 1 unit away. And A is 1, 2, 3, 4 units away, so if I count again, 1, 2, 3, 4, A prime will end up right there. Now, you'll be able to tell if you did this correctly because a reflection's a rigid motion, so these two triangles should be congruent. So if they don't look congruent, try graphing it again. For number 10, in the diagram below, triangle ABC has those coordinates. Graph and label triangle A prime B prime C prime after the translation 5 units to the right and 2 units up, followed by a reflection over the line y equals 0. So let's start at the first one. I'm going to take all these points and I'm just going to go 1, 2, 3, 4, 5 to the right and 2 units up. So that's where C prime is going to be. 1, 2, 3, 4, 5, 1, 2. That's where A prime is going to be. And 1, 2, 3, 4, 5, 1, 2. That's where B prime is going to be. All right, and again, that should be a congruent triangle. Then it says it's followed by a reflection over the line y equals 0. So when my y values are 0, that's just the x-axis. So again, you can just count. A is 3 units away, so if I go 3 units down, I'd find A double prime, B double prime, and C double prime should be 1, 2, 3, 4, 5, 6, 7 units away. 1, 2, 3, 4, 5, 6, 7. And again, you'll know if you made a mistake because all of these triangles should look congruent. Number 11. A regular hexagon is rotated in a counterclockwise direction about its center. Determine and state the minimum number of degrees in a rotation such that the hexagon will coincide with itself. So it's going to land on top of itself. Again, we just take the full rotation of 360 degrees and divide it by the number of sides. And when I divide 360 by 6, I end up with 60 degrees. But now that's not the only rotation that'll do that, but that is the minimum degree rotation. 60 degrees will do it, but so will any multiple of 60 degrees. If I do 60 degrees twice and get 120, it'll land on top of itself. 60 degrees 3 times, 4 times, 5 times, and so on, all the way up to a full rotation of 360 degrees. Number 12. Triangle MNP is the image of triangle JKL after a 120 degrees clockwise rotation about point Q. So I know these two triangles are congruent because that's a rigid motion. So it says the measure of angle L is 47 degrees. First thing I'm going to do is label my picture with that. And N is 57 degrees. Determine the measure angle of M. So that's the first thing we're going to do. Well, if I'm thinking about this as a rotation, L should coincide with P if I were to rotate this back. So I know angle P also has to be 47 degrees. And now if I want to find that missing angle of a triangle, I know the triangle interior angle should sum to 180. So if I do 57 plus 47 to get 104, and then if I subtract that from 180, I find that that missing angle should be 76 degrees. So the measure of angle M in this case is just 76 degrees. Now the question is, how would I explain how I arrived at that answer? Well, you would do exactly that thought process where you would say, oh, okay, so a rotation is a rigid motion, so triangle NPM must be congruent to triangle KLJ. Be careful about the orders of your letters there. N should go with K, P lines up with L, and M lines up with J. And then you would say, since it's a rigid motions preserve distance and angle measure, so the angles must be the same, so angle P is 47, and then the interior angle should be 180, so you subtract it from that to get M. Number 13. The grid below shows triangle ABC and triangle DEF. Let triangle A'B', C' be the image of triangle ABC after a rotation about point A. So I'm rotating about point A, so I know point A is not going to go anywhere. So this is technically the same point as A'. Determine and state the location of B' if the location of C' is 8, -3. So the first thing I'm going to do is count. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. I'm going to connect A to C'. So where is B'? Well, you should notice that between AC and A'C' is a 90-degree angle. So I must have rotated 90 degrees about point A. So what you could do is you could take this side and this slope and just spin it counterclockwise 90 degrees. You know B is going to be somewhere up here, and a quick way to figure that out is just to count the slope. To get from C to B, I went up 1 and then over 4. So to get from C' to B', you can go up 4, 1, 2, 3, 4, and over 1. And when you connect those, you should notice that those triangles are in fact congruent. That's why you should use a straight edge and not freehand it like I did right there. So the coordinates of B' are, let's see, what is it? It's going to be 7, 1. Reason being, it's a 90 degrees counterclockwise rotation about A. And you could tell that because there's that 90-degree angle between A'C' and AC. Now the question is triangle DEF, that one right there, congruent to triangle A'B', C'? Well, if you can describe a series of rigid motions that would map them onto one another, then you'd have an argument for that these triangles are congruent. So I'm noticing that there's this potential line of symmetry at, let's say, x equals -1. So if I reflect over x equals -1, then A would land right on D, B' would land right on E, and C' would land right on F, right? Because they're the same distance away from the line. So you could say that yes, they are congruent because if you reflect over that line, they land atop each other, and a reflection's a rigid motion, and rigid motions preserve distance and angle measure. Number 14. In the diagram of the isosceles triangle below, AB is congruent to CB, so AB is congruent to CB, and angle bisectors AD, BF, and CE are drawn. So if AD is an angle bisector, that means that guy is congruent to that guy, and that guy is congruent to that guy, and CE let's see, where's the other one? BF. So this guy is congruent to that guy as well. It tells me that the measure of angle BAC is 50 degrees. So if it's an angle bisector, I know it's cutting the angle in half, so those two angles are 25 degrees. And it's asking me to find the measure of AXC, so that obtuse angle right there. Well, now the good news is this is an isosceles triangle, so it's got congruent base angles. So I know if this is 25 and 25 over here, these two should be 25 and 25 as well. Now, if I'm just looking at that little triangle right there, I've got two base angles of 25 and 25, and I'm only missing one angle. So if I add those two angles up to get 50, and then subtract that 50 from 180 degrees, I end up with the measure of angle AXC just being 130 degrees. In the diagram below, line segment AB is drawn. Point A has been mapped to image A' by the use of a translation. State and plot the coordinates of B' after the same translation. So A went there, and you could just count the boxes and say, okay, I went up 1, 2, 3 up, and I went 1, 2, 3, 4, 5, 6 to the right. So for B, you can go 1, 2, 3 up, and then 1, 2, 3, 4, 5, 6 to the right. So it looks to me like the coordinates of B' are going to be 9, -1. And if I connect those, I actually am going to use a straight edge this time. And there's a reason why. Of course, you should be using a straight edge every time when you're plotting points. What is the relationship between AB and A'B'? Well, they are parallel. Reason being, if you translate a line segment somewhere else, it's going to have the same slope. So translation preserves parallelism. So you could either say that, or you could say that they have the same slope, therefore they are parallel. Number 16. In the diagram below of triangle ABC and triangle XYZ, a sequence of rigid motions maps angle A onto angle X, and angle C onto angle Z, and AC onto XZ. Determine and state whether BC is congruent to YZ. Well, I think I have enough information here to state that triangle ABC is congruent to triangle XYZ. The reason being is once I read all that, I marked it in my picture, and this to me looks like an angle-side-angle proof, where I've got an angle, a side, and then the angle as well, and that's true for both these. So triangle ABC is congruent to triangle XYZ by angle-side-angle, and if you're thinking about your rules for proofs, if the triangles are the same, the corresponding parts of those triangles should be the same as well. So you can make an argument for BC being congruent to YZ by CPCTC. Number 17. Given the right triangles ABC and DEF, where angle C and angle F are right angles, AC is congruent to DF, CB is congruent to FE, so this and this. Describe a precise sequence of rigid motions which would show that the two triangles are congruent. Well, we run into an issue here where we don't have a coordinate plane where we could just say go right this many and then reflect over this line. So you need to use the letters they give you. There's lots of different ways to do this, but one thing I notice is that point C needs to line up with point F. And if I translated this triangle, just pushed it to the right, so that C landed on F, I'd have the triangle right over here, and then I'd be able to reflect it over DF to get it to land on top of D, E, and F. So what you could say is you could translate point C to F, and then reflect over DF. Notice I used the letters that they gave me, so I just pushed C to where F would be, and then I flipped it over DF. I can't say that I'm flipping it over AC because I've moved AC, so this is technically like an A', C' over here. So be careful with the letters you use there. For number 18, a similar question. it's telling me that the two triangles are congruent, and it wants a rigid motion, so just this one rigid motion, not a sequence, that maps the two triangles onto one another. So again, it looks like if I just reflect over ST, I'm in business. The next part, though, says explain how the rigid motion does the mapping. Well, you could say that the reflection carries S and T onto itself because they're both on the segment, and then it carries point U onto point R because they're the same distance away from T.